inconsistent and dependent systems. Our objective here, we want to identify systems that do not have exactly one ordered pair solution. We've been doing a lot of work with systems that have a nice ordered pair solution, but we know that sometimes the systems do not have an ordered pair solution, and we want to identify those algebraically. So we know a couple of things coming into this video. We know that a linear system, also called a system of linear equations, is two or more linear equations that are working together. For example, here is a linear system in two unknowns, x plus y equals 7 and x minus y equals -1. We also have seen the graphs of these systems, and that graphically, when we have two lines, they can, one, intersect at a single point, which we've worked with a lot. Two, the two lines could be parallel. And three, the two lines could be what is termed coincidental, which means you have one line lying on top of the other. If the two lines intersect, there is exactly one ordered pair solution. If the two lines are parallel, well, they never touch, therefore there is no solution. If the two lines are coincidental, well, they always touch. So therefore there are infinitely many solutions. Okay, a little vocabulary. Math is a language, lots of vocabulary. When a linear system has one ordered pair solution, we call that system consistent. When a linear system has no solutions, in other words, the lines are parallel, we call that system inconsistent. And finally, when the linear system has infinitely many solutions, the one line on top of the other, a coincidental case, that system is called dependent. All right, so we've worked with this one, and now we want to look at how these two, the inconsistent systems and the dependent systems, look when we look at them algebraically. Okay, what's going to happen algebraically when we look at those two types of systems? So, in other words, let's see what happens with the inconsistent and the dependent system solutions if we use the substitution method or the addition method. Okay, so example number one here, the bottom of the paper, we have two systems, 4x plus 6y equals 12 and 6x plus 9y equals 12. And we want to solve it, and I'm going to solve this using the addition method. So I'm going to write the equations down here. 4x plus 6y equals 12, and then 6x plus 9y also equals 12. And I'm going to look at these and I'm going to say, well, hang on a second. In order to use the addition method, I need opposite coefficients of either the x variables or the y variables. A little easier to see the opposite coefficients for the x. The lowest common multiple is 12. So if I multiply the top equation by -3 and the bottom equation by +2, I will have opposite coefficients. So the top equation, I'm going to multiply it by -3. The bottom equation, I'm going to multiply it by +2. And I'm going to come up with, let's see here, this is -12x. -3 times +6 is -18y. And -3 times +12 is -36. Multiply the second equation by +2, I get 12, 18, 24, all positive. So I have 12x plus 18y is equal to 24. And now I can do addition. Well, I chose 3 and -2 to get rid of this, but lo and behold, it got rid of that because that's a 0, but it also got rid of this. And so when I add, my solution is 0 equals negative 24. Okay, so what does that tell me? Let's write this down so we can see what this is in words. A resulting statement. Notice I have no variables. A resulting statement, which in this case is 0 equals negative 12. That is never true, right? 0 equals negative 12 is not a true statement. It's never true, okay? A resulting statement that is never true indicates, hope I spelled that right, that the system has no solutions. Okay, in other words, there's no solutions. As we know up here, no solutions, it is inconsistent. So it is inconsistent. In other words, the lines are parallel. Okay? So we have a resulting statement, 0 equals negative 12. And we know that's not true. That's not true anytime. Okay? So it's never true. It indicates that this system has no solutions. It's not true, so it has no solutions. A system that has no solutions is called inconsistent. And we know that when it has no solutions, the lines are parallel. Okay, I got to put parentheses around that. In other words, zero never equals 12, no matter what x and y are. Okay, pick any x value, any y value you want. You will get a statement that's not true. Okay, no matter what x and y are, you're going to get an untrue statement, and that indicates to you I have no solutions. It's inconsistent. The lines are parallel. Let's take a look at an example algebraically when we have a dependent system. So give me just a moment here. Okay, so here we go. Example 2, solve the system. The first equation is y equals 3x minus 2, so that's written in y equals form. The second equation is negative 15x minus 5y equals 10, and that's written in general form. So let's use substitution to solve this one. I'm already told that y is this, so let's put 3x minus 2 in for y. Okay, so I'm going to put 3x minus 2 into equation number 2. So it's 5 times 3x, whoops, I need an x on that. 3x minus 2, and that equals 10. And so I substituted 1 into 2. I'm going to solve this using the substitution method. Let's do some work here. I got to do a little distribution. So negative 15x, negative 5 times negative 3x is negative 15x. Negative 5 times negative 2 is positive 10. And negative 15x is minus 15x is 0. I get 10 equals 10. Well, that's always true. No duh, 10 equals 10. So, when it's an always true statement, that means it has many, many solutions. So let's write this down. A resulting statement, and the resulting statement in this case is 10 equals 10. That is always true. Indicates the system has infinitely many solutions. Okay, the system is dependent. It is dependent. Okay, infinitely many solutions. It is a dependent system. In other words, lines are coincidental, which means a fancy word that means the lines are on top of one another. Okay, again, in other words, 10 is always 10. X can be whatever X is. Y can be whatever Y is. No matter what happens, 10 is equal to 10. Okay, so, in other words, ten is equal to 10, again, in this case, no matter the values of X and Y. Okay? So that's what you're going to see algebraically when you're running across inconsistent systems and dependent systems. So let's summarize that briefly here. Untrue statement is telling us we have an inconsistent system, parallel lines. A true statement, like 10 equals 10, tells us we have a dependent system and we have coincidental lines. That's the, whoops, if I can spell lines. There you go. So that's, if you have an untrue statement, for example, 1 equals 5, we have an inconsistent system. Those two lines are parallel. 1 is never 5, so those lines never touch. If you have a true statement, for example, 10 equals 10, that's a dependent statement. 10 always equals 10, so we have coincidental lines, and those coincidental lines and those lines always touch. And that's how you want to remember it.